Welcome to VRC Smart Edu channel. So today we are here with chemistry, organic chemistry, chapter 10, haloalkanes and haloarenes. This is already part 2 book from your NCERT. We are starting the first chapter. So this is a part 3 video of this chapter. So the rest of the two parts, the links are provided in the description. You can go and check it out. The previous part link is popping up here. You can go and check it out. So watch it for complete clarity. Now we are going to start with the new part of this chapter, that is going to be the chemical properties of haloalkanes. In that, first we are going to look after the nucleophilic substitution reaction. Let's see. Okay, let's go in detail. Now come on. See, whenever we talk about the chemical properties, we have divided the chemical properties into three different categories. Okay, chemical properties of haloalkanes we are seeing. Chemical properties of haloalkanes are divided into three. One is going to be the nucleophilic substitution reaction. Next one is elimination reaction, and third one is reaction with metals. This one is very important to remember. Okay, so the chemical properties of haloalkanes. This is only for haloalkanes. Okay, so the chemical properties of haloalkanes are divided into three. One is nucleophilic substitution reaction, elimination reaction, and reaction with metals. So now the nucleophilic substitution reaction is divided into two. Okay, your first one is SN1 reaction, your second one is SN2 reaction. You will write something like this: SN1 reaction, SN2 reaction. Clear? We will deal with it very detailed in the future part of this chapter. That is, in this same video we will deal with. Okay, before going, let us just look after what do you mean by nucleophilic substitution reaction. So first of all, let's understand what you mean by nucleophilic substitution reaction. Okay, so nucleophilic substitution reaction is nothing but you have a nucleophile. Nucleophile is nucleus seeking. So you have a nucleophile. So nucleophile, what they will do is, here in this reaction there will be one nucleophile already existing. That will be replaced by another nucleophile. That's it. In this reaction, already whatever the nucleophile is present, that nucleophile is replaced by the another nucleophile. Okay, the reaction in which a nucleophile replaces the already existing nucleophile in a molecule is called as nucleophilic substitution reaction. This already word is important. So now let me give you an example so that you can able to understand it very easily. Okay, listen carefully. Now we are having the reaction OH minus plus C H H H X. Now after this reaction is going to occur, what is the product that you are going to get? What is the product that you are going to get? Your product is nothing but, listen carefully, this is nucleophilic substitution reaction. That means your nucleophile from the reaction will be removed. So this is your nucleophile. This will be removed, and the newly coming nucleophile will take the place of this old nucleophile. Clear? So how will you get your product to be formed? You will get your product as, listen here, product is C H H OH H plus X minus. This will be your product. So already present nucleophile will be replaced by another nucleophile. That is called as nucleophilic substitution reaction. So the nucleophile can be, what are the nucleophiles you can able to observe? I'll write the list of that so that will be easy for you. The nucleophiles you can observe can be bromine, iodine, cyanide, nitride, then any alkane with O. Okay, So these are the things you can able to observe as nucleophiles. Clear? So bromine, that is Br minus, I minus, Cn minus, NO2 minus and RO minus. Clear? Yes. Now moving on to the next. Next what we are going to see is about the ambident nucleophile. What is the thing that we are going to look after? We are going to look after about the ambident nucleophile. What is ambident nucleophile? Ambident nucleophile. See, ambident nucleophile means they have two nucleophilic center. So we saw that what is a nucleophilic substitution reaction. One nucleophile will be substituted by the already existing nucleophile will be substituted. That is, instead of that, another nucleophile will be placed. But here, groups like nitrates and cyanates possess two nucleophilic centers. That is, you have to just remember, whenever two nucleophilic centers are there, then it is called as ambident nucleophile. Remember, ambident nucleophile, two nucleophilic center. This one you have to remember. Two nucleophilic center will be there. Clear? Let me give you an example. So listen carefully. Okay. So first we are going to talk about the cyanide group. So I told groups like cyanide and nitride. So first we are talking about the cyanide group and then we will go to the nitride group. Okay. So first in cyanide group, you have, I told, two nucleophilic centers. So I'll divide it into two. Okay. So one is going to be R with the Cn attached. Another one is going to be R with Nc attached. See how much difference you have. This is called as alkyl cyanides. Alkyl cyanides. This is called as alkyl isocyanides. Alkyl isocyanides. See how much difference you have between the both. Clear? Next, another example let us look after. Okay. Now we are going to look after about nitride. So I told it is also having two nucleophilic center, dividing it into two. So first we are going to have RNO2. Again here we are having RONO. So this RNO2 is called as nitroalkanes. Nitroalkanes. This RONO, this is called as alkyl nitrides. Alkyl nitrides. Clear? Hope you got it. Now let's move to the next. So now we are going to deal with SN2 and SN1 reaction. So here we are going to see it in the form of a comparison. Okay. So in your examination it can be asked in terms of comparison, or they may ask you to only explain SN2 reaction or only SN1 reaction, or there is some problems that you are going to solve based on SN2 and SN1 reaction. Okay. So now let us see the points. So first point is going to be nucleophilic substitution is in SN2 reaction. Remember, nucleophilic substitution is bimolecular. It's bimolecular reaction. So if it is bimolecular reaction, then here it is going to be unimolecular. Nucleophilic substitution is unimolecular reaction. What is the meaning of bimolecular and unimolecular? Bimolecular means involvement of two molecules, two different atoms. Okay. Unimolecular means only one atom. Okay. So already we saw an example, replacement of only X atom. That is called as unimolecular. If it is going to be the replacement of X means chlorine, bromine, or any one atom you are going to replace, that is going to be unimolecular. Any two molecules you are going to replace during nucleophilic substitution reaction, it is going to be SN2 reaction. Next, second one, it follows second order of kinetics. It follows second order of kinetics. It follows first order of kinetics. Next, third point, the rate depends upon rate of reaction, or you can say rate depends upon the concentration of both the reactants. Here rate depends upon the concentration of any one of the reactants. So reactants in the sense you have on the opposite side, you will be surely having two reactants, then only the reaction can take place, or else you should have a catalyst. So the rate of reaction here depends upon both the reactants that you have. Here the rate of reaction, that is the rate, depends on only depends upon the concentration of, depends upon the concentration of only one reactant. Only one reactant. Okay. So next, the fourth point that you can have here is no intermediate is formed. No intermediate is formed. Your intermediate is formed. Your intermediate is formed. Next, fifth point, let us see. Fifth point is going to be, just listen here, it is going to be the single step reaction. This is going to be the single step reaction. It is going to be the two-step reaction. It is going to be the two-step reaction. Okay. Sixth point. Okay. So, the same example you take OH minus plus. So, I told what is going to happen here. Bimolecular reaction and unimolecular reaction we just learned. So, listen here. What is happening here, C is there and you are having H, H, H and X is attached. So what you got as a product, C, H, H, OH, H plus X minus you got, right? So in this reaction, see one molecule is replacing the another molecule, so bimolecular reaction. Here if you just take the example, okay, you will get the example as CH3, C, CH3, Cl, above here CH3 is there. Okay, so what you are going to do is, so here intermediate step is going to happen. This intermediate step is a slow process. It is a slow step. Okay, it is a rate determining step. Okay, now what is going to be formed is here your C, Cl, CH3, CH3, CH3. So this is the cation that is formed, that is the anion, and this is a cation that is going to be formed. Clear? So positive negative is formed. Now second step, I told it's a two-step reaction. So second step will also take place. What is going to be the second step? So actually here the Cl is going to be replaced by OH. Cl is going to be, that is CH3, C, CH3, CH3, and here OH will be replaced, OH minus. Okay. So this is a two-step reaction. This is the step 1 and this is the step 2. Clear? Alright. Next, seventh one. Okay. Inversion of configuration takes place. Inversion of configuration. I write config. Okay, configuration takes place. Retention of configuration to some extent. Inversion. That is, you can able to observe only inversion here, inversion configuration here, but here you will observe the retention configuration to some extent. That is, to some limit you can able to observe the inversion here. Okay. Next, final point. So the final point is going to be, the eighth point, final point is going to be order of reactivity. Order of reactivity. Both the areas. Order of reactivity. Okay. So your order of reactivity is, listen, it is going to be CH3X. CH3X will be greater than 1 degree, greater than 2 degree, greater than 3 degree. Here opposite, 3 degree, greater than 2 degree, greater than 1 degree, greater than CH3X. So for 1 mark solving 1 mark and for solving various types of problems, this order of reactivity will be very helpful. Clear? So next we are going to look after the stereochemical aspects of nucleophilic substitution reaction. Under that, the first one we are going to look after is optical activity. So optical activity, here I am going to explain you with the help of a diagram, but you have to write it in terms of words. Okay, be careful with that. So whatever I explain in the terms of diagram, you can write it in the terms of words. Okay, listen here. So first you are having a Nicol prism. Okay, initially you are having a Nicol prism. So imagine this is your Nicol prism. I'll draw it. Okay, imagine this is your Nicol prism. Okay, I'll write Nicol prism. Clear? So when you are going to pass a white light, okay, white light. Okay, when a white light is passed through the Nicol prism, it becomes plain polarized light. So it will be emitting as a plain polarized light. Okay, so this light is about to pass through the solution of certain compound. So now this light, this plain polarized light is there, no? Now this plain polarized light, when it is allowed to pass through any of the solution will be getting rotated. If it is passed to any solution, the solution will be getting rotated. Okay, so such compounds are called as optically active compounds. Such compounds are called as optically active compounds. Listen carefully. You are having a Nicol prism. When white light is passed through the Nicol prism, what happens? The resultant light is a plain polarized light. When this plain polarized light is allowed to pass in any solution, what happens? The solution will be getting rotated. So, such solutions are called as optically active compounds. Clear? So now we talk about the rotation. If we talk about the rotation can be taking place in two directions. Rotation can be take place in two directions. Okay. So if the rotation, listen carefully, if the rotation is going to be taking place in a clockwise, direction, it is known as dextrorotatory isomer. Dextrorotatory isomer. Okay, I'll write the spelling here. Dextrorotatory isomers, or it can also be called as positive isomers. Positive isomer. See how many names? Clockwise, dextrorotatory, clockwise or dextrorotatory, or positive isomer, or it is also called as right hand side. Right hand side. Okay, see, two types of direction it has. If it is going to be a clockwise direction, then it is also called as dextrorotatory and positive isomer and right hand side. Okay, if it's going to be the, I'm going to write here, if it is going to be the anti-clockwise. Anti-clockwise, or it can be called as levorotatory, levorotatory, or left hand side, or negative isomer. Negative isomer. Clear? So that's all about this. So the types of rotation you have to remember, and when it's passed through light, what happened, that and all you have to remember. Clear? These things you have to write it in terms of words, that's all. Okay, now let's move to the next. So now let's move to the second one. It's going to be chiral or chiral carbon. Okay, chirality or chiral carbon. Okay, so listen here. The object which are non-superimposable. Non-superimposable means on the mirror images when you see, it will not be having the same reflection. Okay, so that are called as non-superimposable. For example, you just see carbon you are taking and you are attaching the OH, H, OH, H. Now, if you are going to divide this and place it in the mirror, if you place the one side of this mirror, the same will be reflected on the other side of the mirror. The same, this one will be reflected. So this is the superimposable images. If it is going to be non-superimposable images, then here Cl, here Br, here H, here OH, if all are different groups are attached, then if you divide it, okay, whatever the groups here are not the same here. These are the non-superimposable images. Clear? So as it is, it should reflect as a mirror image, then it is superimposable. If it is not reflecting like that, then it is called as non-superimposable images. Clear everybody? Okay. So objects which are non-superimposable on their mirror images are known as chiral object. Non-superimposable. This is the keyword. What is a chiral object? The objects which are non-superimposable on their mirror images are known as chiral object. So the phenomenon, this thing, if it's going to happen, is known as chirality. Chirality. Okay. So all optically active compounds are chiral compounds. The same opposite will be achiral or achiral compounds. Okay, so listen here. The objects are here superimposable. That's the difference. Here non-superimposable, here superimposable. On their mirror images are known as achiral compounds. This phenomenon is known as achirality. The same. All optically inactive compounds are achiral compounds. Here active compounds, here inactive compounds. So whatever you write here, the opposite to be here. Clear? Now moving on to the next is given as symmetric carbon. Symmetric carbon means if two similar groups are attached to the carbon in the given compound is called as symmetric carbon. Okay. So carbon is there. Carbon should be placed with same group like this. Then it is symmetric carbon. Okay. So asymmetric carbon. What is asymmetric carbon? Different groups are attached to the carbon in a given compound is called as 1 minute. Asymmetric carbon. It is usually represented with hashtag the star symbol. Okay, the star symbol. So this carbon is going to have the different compounds attached to it. Different compounds attached to it. Then it is called as asymmetric carbon. Clear? What is enantiomers? Enantiomers. Okay, enantiomers. The stereoisomers related to each other as non-superimposable mirror images are called as enantiomers. Okay, non-superimposable. They are looked as non-superimposable mirror images. They are called as enantiomers. The mixture, then racemic mixture. What is the racemic mixture or racemic modification? A mixture containing two enantiomers. That is, this is an enantiomer, right? So it is a stereoisomer which is related to each other. They will be related to each other as non-superimposable mirror images. Okay, that is important. Okay, equal proportion they will be present. Mixture containing equal proportions of two enantiomers. They will have zero optical rotation. Okay, optical rotation will be 0 and the rotation due to one isomer, that is, see if one isomer is rotating, if the another isomer is going to rotate like this, one isomer and another isomer rotation will be cancelled and it is going to become 0 rotation. That is what? One isomer cancelled by the rotation due to the other isomer. So only they have the 0 rotation. Clear? So such mixture is known as racemic mixture. Example, butane to all. Plus or minus butane to all. It is a racemic mixture. Clear? Plus or minus butane to all. To be clear, I will write here plus or minus butane to all. Okay? Okay. So, thank you so much for watching this video. If you have liked this video, kindly like it and share it with your friends and family. And if you have really enjoyed, kindly share it and subscribe our channel and click the bell icon for notification. And follow us, our channel, for more videos. So we'll be upcoming with future videos also. So till then, thank you and bye.